as far as that's concerned. And he's going to uh, present from his screen from his computer. So hopefully this all works out well. So the way this is going to work, I'm going to go ahead and stop and mine here. Stop sharing mine. And without any further ado, Mr. Hogg, if you can go ahead and share your screen, or if you want to say something, give a little quick introduction about yourself first, and then start with your presentation.
Great, will do. Can you hear me okay, Alex?
Yes, you are hearing just fine.
Great, and I see the infinitely recursive screen there, so it looks like my screen is coming through.
It is.
Great, so I'm all set here. Hello, everybody out there. Thank you for having me and being willing to listen to what I have to say here. Like Alex said, my name is Robert Hogg. I work at the Jet Propulsion Lab in Pasadena, California, and that's one of the NASA centers. And I'll tell you more about JPL later, but the short version is the Jet Propulsion Lab is to explore the solar system with robots and robotics. So it's the unmanned exploration of the solar system. I'm just going to jump into some content here so that we can get going, and then I'll show you some videos and some other presentations, and then we'll have time for questions. I'd like to hear your burning questions. So I will start with one of the first projects that I worked on here at JPL, the urban robot. The focus of that project was perception and autonomous navigation. Autonomous means directing it or doing things by itself without human control. And so when you're exploring space, that's very important because of how long it takes for radio signals to get to our spacecraft and our rovers on other planets. This rover was not going anywhere other than Earth. It was actually meant for a DARPA project for reconnaissance. But we were able to use a lot of what we learned in autonomy with this rover on other Mars rovers. And this project was going on years ago. So just some basics in robotics that I thought I'd show you folks, and for anything you're not familiar with. A robot is simply, we'll call it my definition, a computer that can interact with the physical universe around it. So for that you need a chassis with motors, with appendages, with pieces of metal that you can do something with in the physical world. And then you also need the computer itself, so processors, and then also sensors to sense the environment of the rover or robot to then be able to make decisions. So these are the kind of basic components of a robot. At JPL, we've worked a lot with, and many companies and institutions now are using cameras as one of the main ways of perceiving the environment. And we use stereo cameras because just like your eyes, that gives you an idea of how far away things are, the range of things, not just what's being seen. And we also, in this research project, did a lot of work with LiDAR, which is a laser radar. This was all 15 years ago, and now all these things are kind of standard fare for all the autonomously driving cars that you hear about every day from Google and Uber and everybody. So they're using LiDARs and stereo cameras to perceive what's happening in front of the car. We also messed around with infrared cameras, and this gives you an idea of how you see range, or how far away things are out the front of the rover. These are the two different cameras, and all the processor is doing is comparing 2 pixels in each camera, and the different perspective, because the cameras are a certain distance apart, you can tell how far away things are. And then from that, you can see how far out things are, and then make a kind of an obstacle map of what's in front of the rover, and then do some planning on what you want to do with where obstacles are. So I'm going to cut to a video here. Hopefully this comes through okay. To give you an idea of, so again, this is a really old video, but this will show you in real time everything I just described. After about 18 months of work, this robot will drive down this hall by itself. So what I told it to go straight, and so it's just going to try and go straight unless it gets perturbed or stopped by an obstacle. Can you change that timer to 130? 2001, making me feel very old too. So this is one of the first projects that I had at JPL that I wiggled my way into working on, and I started as a software programmer, and then I ended up being the chief engineer, and then I ended up running the whole research task. So there you go. That happened in real time. So I would claim that if you gave a teenager who's played 10,000 hours of computer games, I've played computer games, and they tried steering that robot from inside, from first person view with the camera, that they would not have been able to avoid all those boxes as well, fast, and as smoothly as that robot did by itself. Then we did lots of other path following behaviors. We got this thing climbing stairs autonomously by taking a camera image and looking for parallel lines in the image, and then you can tell which direction the stairs are tilted, and then tell the rover to climb or steer one way or the other. And so this is the user interface that we put together, and you can see the stairs are called out here in parallel. And I think that's it for that presentation. I'm going to move on to the next rover, or the next project that I wanted to show you. At JPL, there's an advanced technology office, and so I won a small amount of money. Small in this business at that time was $100,000, and I hired 5 students. One was a postgraduate and some summer interns, and with $100,000 over a 1-year period, we put together this spider bot. The idea was to make a web of sensors with legged robots that could do a better job of walking around in terrain than with wheels. And so again, you start with a processor, a little radio for communication. That's a small radio next to a penny. And this is years ago. This is an electronic camera. And then we had the mechanical engineering student design the legs out of rapid prototyping, which lots of folks have 3D printers on their desks now. And we put together a mechanical design to be able to walk. And so if you have 3 legs and a tripod, then the other 3 legs can move. So you can have 2 tripods taking turns walking, which I'll show you in a second. And before we built anything in the computer-aided design program, the CAD program, we looked to see how well this robot would be able to move and the range of motion of the legs. And then we sent the designs off to a rapid prototyping shop, and with a very small amount of money, back came these rapid prototype plastic pieces, and we put the thing together and tested it out. And so then that project carried on for a couple of years after that, and we did a version where we were climbing on a mesh upside down to be able to do things like repair fixed arrays out in space. So instead of having to have an astronaut go out and do repair, you can have a legged robot walk across the mesh and do repairs with little tools at the end of its legs. And so I will show you another video here. And hopefully these videos are coming through okay for you.
They're coming through great.
Excellent, thanks for that, Alex. I called it the Micro Robot Explorer, and then the outreach people at JPL decided to call it a spider bot. So this is 1 leg. So that's just 3 regular servo motors with 1 leg. And these are 6 legs together. And then this is the thing walking with, you can see a power cable, and So I think I'll walk through this again after the intro here. I just remember there's an intro, and so I get to talk to each part here. So, all right, there is one just regular RC car um, motor. It's a servo, and then there's two in motion, and now there's three in motion. If you just move these three motors together, you get this very crazy design that looks like, you know, an animal leg running along. And then we put them on a stand, put 6 legs on it, and did a range of motion test. So the programmer put it through its paces, and it turned into this little robot dance that we got a big kick out of. We were not expecting this. And so this is all before, this is, you know, a few days after we got all these pieces and put it together. And those are solar cells on the legs. We ended up not using those because there's not enough power for what these motors needed, but the idea would be that a future rover with more efficient motors and better solar cells, we could use that space. And then this is walking across a table. It's like somebody's telling me that I'm missing a meeting. I already told them that I would not be able to be there. And so we're doing a walk across the Mars yard at JPL. And so this is with power coming from the power cable off to the left. And now finally this is everything together with completely wireless. So power is on board with lithium ion batteries. And the radio is receiving commands from us remotely. So everything's together. It's no cords. And so we just did some basic walking around the Mars yard. And so let me skip ahead here, see if there's anything else I want to show you. So we ended up doing a little demo where we pretended like a network of radios could pass information across the surface of Mars or another planet. And if one of the radios broke, so this is a rover deploying the radios across the Mars yard. And then if one of the radios broke, which is one of my engineers walking out and turning off the radio, then we send out our little spider bot, and it replaces that radio connection by itself if it was autonomously walking across Mars or somewhere else. So I mentioned earlier the media people called it a spider bot, and I said, you know, spiders have 8 legs, and they said, okay, great, and they headed off and called it a spider bot anyway. And so they were right, I was wrong, because then of course it got headlines and JPL spider bot, but we really only needed 6 legs for what we were trying to do with this. So those are some of the early projects that I worked on, and I got into those by just getting over here and starting as an intern, and then talking to lots of folks about what people are doing, and you know, being in communication. So I'll talk about that in a second. The next thing I wanted to show you is, well, actually, I'm gonna start on that now, and I'll flip back and forth here between some slides. So just bear with me. So I don't have a lot of graphics to show you here, but hopefully we have all of our audience by now, or the folks who are going to be able to stick around. I wanted to just give you about a 4-minute description of how I got here, because I think there's some similarities that you'll see on where you're at and what you're working on. So it's a very long story, but I'm going to cut some of it short, but not too short. When I was younger, I was trying to figure out what to do with myself, and I kind of got interested in robotics, and I decided I could make robots that run themselves and make like a vacuum cleaning robot that helps lots of people. So I make this design, I hand it off to manufacturing folks, and they make 500,000 vacuum cleaning robots, just like the Roombas that exist today. And in fact, I worked with those guys at iRobot before the Roombas existed on some of their stuff. And so that was my solution to life when I was, you know, 11, 12 years old, and so that got me interested in programming and technology in high school, and I did backpacking and all sports and all kinds of other stuff, but I was working on programming robots when I was in high school. I went to a private school that was not great on setting people up to go to college, to make a long story short. So I decided to go to college very late in the game. I was thinking of just going out and trying to start a company and just start work in different areas, and I realized that there was stuff, labs, uh, bleeding edge ideas and technology that I would not have access to if I didn't get to a 4-year school at least and go for it. And I decided that in my senior year at college, and which is way too late. And so I was missing a ton of math that I needed to start working on an engineering degree, and a ton of physics. So my solution was I went to a community college. I went to Pasadena City College in Los Angeles, and luckily they had a pretty good math department, pretty good physics department. I just caught up on math all the way up through all the calculus classes, starting from pretty low, kind of minimum high school requirements, for a couple years, and I got lots of my other general ed stuff done, chemistry and English, etc. Some of the 2-year stuff for a 4-year degree. And that was at Pasadena College, about 5 miles from where I'm sitting here. And then I applied to a bunch of different colleges to transfer, and got accepted to some of them, not all of them, and I ended up transferring to UCLA, University of California, Los Angeles, to finish my engineering degree and actually start studying engineering. There wasn't really engineering classes at Pasadena City College, and that worked out great. Actually, side note, at UCLA, because I was so interested in robotics, and this little story might or might not apply to you and your college careers there in the future, but I discovered at UCLA there was not a robotics major that I could major in for undergrad. There was a few things happening at Carnegie Mellon and other places, but it wasn't as hot as it is now. And also, robotics uses mechanical engineering, electrical engineering, and computer science, all three, to make these different systems and vehicles and autonomous robots. So I was trying to solve how to study all three, even though I had to pick a major. My solution was I picked computer science and electrical engineering, which is, kind of a standard engineering major out there. Sometimes it's called computer engineering, sometimes it's called computer science and engineering, but I got lots of computer science classes and lots of electrical engineering classes, but I was missing mechanical engineering. And so there wasn't a regular way to do this, but I ended up petitioning my undergrad dean, the professor in charge of the undergrad school, and swapping out computer science classes that counted for my degree that I was not interested in because they didn't have anything to do with what I was going to be working on, and I switched them with mechanical engineering classes. So I switched 3 regular curriculum computer science classes for 3 mechanical engineering classes, like computer controlled machines and some other things, and that worked out great. And so the reason I felt I needed to do that was to back it up. I had a reason for being there in those classes because I had decided I was going to make these robots. So my advice to you, there's a couple things here. One, if you have some idea, whatever it is, of what you want to make or create when you are done with college, a medical device to help people, or a new way of doing business, or if you really want to help people be healthy and well as a doctor, or whatever it is, if you have some idea of that end result of your work after you're done with college, the end result of your work after college, then you can keep that in mind as you're going through your classes and making decisions during your education, and you'll actually retain what you're learning better because you're going to have some idea of what to do with it instead of just memorizing it and spitting it out on a test paper and then it's gone forever. So just to finish the story, I got my 4-year degree at UCLA, so Pasadena College, UCLA Engineering School, and I applied for internships at different places. I ended up getting an internship at JPL. I had to turn down one that, I had to make the decision to wait to see if JPL was going to accept me before that decision was done. And luckily, I got an internship at JPL in my senior year at college, and I got hired full time after that. And so I've been working at JPL since 1997. Again, makes me seem very old. I took a hiatus and went and worked for a nonprofit for a few years, and then came back to JPL to work on Mars robots after all these research robots I've been showing you. So I hope you caught some of that on the trajectory I took. And so, a couple more points for you. You decide you want to work on a particular area or a type of technology or whatever it is, there is nothing that can stop you. I'm sure you've heard this before, but it's all about persistence and just continuing to be in communication with people on where you're trying to go and what you're trying to do, and just keep at it until you get there. Okay. So I'll end off on what happened with me there, and we'll go back to some slides and videos. So moving on to Mars robots. After my hiatus with the nonprofit, I came back to JPL and started working on the Curiosity rover in 2008. And rather than show you a bunch of slides, I'm going to start with a movie here. Video. So worked on the motor control system for the Curiosity rover. That was my job, the systems engineer for the motor control system for the Curiosity rover. So my motor control system ran the control of the 32 motors that are on the rover and the 8 motors that are on the landing engine. I'm going to try and speed it up here so that you guys have, you folks, guys and gals, guys and girls, have time for questions. So we engineered this thing, we sent it to Mars. You'll get an idea of the phases of that in the next presentation I'll show you, but this is what happened on landing day in August 2012. Is it 2012? When the Curiosity rover landed on Mars.
Things are looking good. Coming up on entry. Vehicle reports entry interface. At this time, it'll be pressurizing the propulsion system to increase the thrust of the system. It'll use that for all the maneuvering in the atmosphere we're about to do. We're standing by for guided start of guided entry.
So this is entry, descent, and landing of the spacecraft in the Martian atmosphere.
To feel the atmosphere as we go in here. The vehicle has just reported via tones that it has started guided entry. At this time, the vehicle is beginning to steer its way to the target. We have seen peak deceleration. That is starting its first neck reversal. It is reporting that we are seeing G's on the order of 11 to 12 Earth G's. Neck reversal 2 is starting. We are now getting telemetry from
Telemetry from Odyssey. It was in communication with the Odyssey orbiter, so we could get data coming back during into different landings to the orbiter. So the parachute came out, the heat shield came on.
We found the ground expand. We're down to 90 meters per second at an altitude of 6.5 kilometers descending.
And that's the rover touching
Standing by
there,
for backshell separation.
the entry capsule. And then the parachute's released, and
We are in hard flight.
Retro rockets.
We're at altitude of 1 kilometer descending.
That's the descent engine with eight rockets. And then, so that we don't pick up too much dust and for many other reasons, we had to put together this sky crane to lower the rover on cables and let it touch the ground. And then the landing engine drives away, and we were very happy. And because of the internet and web streaming, this is the first time that anybody, anywhere, is able to watch this whole thing happen with us.
Got thumbnails.
And this is the very first image that we saw on that day. All right, so that was landing day. So I think you guys had a slight hard time hearing me talk while that was going, but I just wanted to say a couple things. Number one, this is a big kick for me because I was there in a blue shirt in the surface room where that first image came down after landing. And just to put that in perspective, imagine working on something for 5 years. You're designing this thing, getting it built, and testing it like crazy, and then these 7 minutes, we call it the 7 minutes of terror. It comes down to those 7 minutes on whether it's going to live or just turn into another crater on Mars. And so I was standing there going, I'm either going to have a job tomorrow and for the next year, or I'm going to have to find something else to do if this doesn't work. So it was a big win, big success for everybody. And the other fun thing for me is all these folks that you see here. I recognize about 100 people in this video because I worked with them at the time, and a lot of them are working on the current project that I'm working on now. So it was a big win for us and everybody involved. I'm going to hustle here so we can get to some questions. I'm going to show you kind of what happened on the first 30 sols after everything that you saw happened. A sol is a Martian day. A Martian day is 40 minutes different from an Earth day. Just so that we understand each other, we call them sols. So we landed. Everybody was very, very happy. This image was taken by the Mars Reconnaissance Orbiter, which is an orbiter around Mars that was already there. And we were lucky enough to point the cameras as it was going by overhead and caught this image of, within those 7 minutes, of the Curiosity lander coming down. So you can see the parachute with the lander. And then this is a still shot of what you caught for a second there of the downward facing cameras on the bottom of the rover catching the inside of the heat shield falling away right after the heat shield separated from the landing vehicle. And these are all the different pieces that landed on Mars, and the rover is right there in the middle. The back shell, the parachute, and the sky crane, and the heat shield way over there. And some of the scour marks of the landing engines from the rover landing. This is the very first image that we got with a lens protector on the rover, and so this was the first visual indication we had that the rover landed. And that's our rover's shadow sitting on the surface, and then some of the amazing images from the environment around it. So that's what happened in 2012, and then we continued to head towards Mount Sharp, which is in the distance there, taking measurements with all the different science instruments and drilling samples. And this is the sampling hardware at the end of the robotic arm. And so this is one of my favorite pictures because you can see this is taken from the arm unstowed and pointed at the belly with this telescopic imager. So it's a stitched together picture panorama of our rover sitting on Mars, and it's just a cool view. So this went on to explore Mars, and it is still going. The nominal the lifetime of the vehicle is supposed to be 1 Martian year, and we just passed 2,000 sols, 2,000 Martian days that Curiosity has been operating and doing great science. And so it discovered clay that was not too thick and not too salty and could sustain life, which we didn't know if there was anything like that in existence at that time over there. So now I'll switch over to my last presentation. I think I have one more movie. Let me just check. Yeah, so let's see. Yeah, one more. Okay, so I am currently now working on the Mars 2020 rover, and looks like I've got enough time to get through this. JPL has been sending spacecraft out to explore the solar system for many decades now. We actually landed 2 landers on Mars in the 70s and sent 2 spacecraft out to the outer planets in the 70s. The Voyager spacecraft are out past the edge of the solar system. We're getting there. These are all the Mars vehicles that are either on Mars operating or will be there soon. InSight, the InSight lander, will be landing shortly. And then Mars orbiter from China. And so the European Space Agency and others are getting in the act here. It's not just, won't be just JPL soon running rovers and orbiters around Mars. And I'm working on this one, the Mars 2020 rover. And also the Europeans are landing ExoMars, or launching ExoMars in 2020. The Mars 2020 rover is, so we'll start with science. Explore the ancient environment on Mars, assess the habitability of the ancient environment on Mars, get samples, and then we're going to collect samples inside the rover, cache them, it's called. So this is the beginning of a sample return mission for bringing the samples back to Earth. And then we have a oxygen generation experiment to prepare for humans to visit Mars, and that takes CO2 from the environment and makes oxygen from it. This is an example of being able to recognize potential biosignatures, lifelike patterns in a rock or a rock outcrop. And so we have 2 spectrometers, 2 instruments at the end of the robotic arm that's specifically designed to be able to analyze features like this. And I mentioned this is the beginning of a sample return mission. We've never brought samples back from Mars before, and for science reasons, it's really, I was talking to the deputy project scientist the other day about this. Basically, we'd have to ship roomfuls and roomfuls of equipment up there and, you know, do peer reviews of the science to, beyond a doubt, say yes or no on some of these scientific discoveries that we're making. So the solution is to bring the samples to Earth and send those samples around the world and have scientists at different locations around the world do their analysis on them. And so Mars 2020 is going to land, spend 1.25 years collecting up samples, somewhere between 20 and 30 samples, and then dump them on the ground somewhere or keep them inside, and then meet up with a retrieval rover, which will then take the samples and launch them in a MAV and send them up to an orbiter and rendezvous in orbit around Mars, and then bring those samples back to Earth. So that will happen a few years after the Mars 2020 mission lands. So 2 or 4 or 6 years after, then those samples will be brought back to Earth. And then, as I mentioned earlier, we have this oxygen generation experiment so that our future astronauts on Mars will have hopefully a little unit that they can use to breathe while they explore. So some more about the mission. It has a launch phase. The entire JPL's entire part of this is housed in the little nose cone of that rocket there, and then we have a contractor that provides a launch vehicle. And the cruise phase, which you saw some of in that animation, takes about 8 months to get to Mars from Earth at I think it's tens of thousands of miles per hour. I'll have to double check that. And then the entry, descent, and landing phase, which you saw, those 7 minutes of terror. A lot needs to go right in 7 minutes, and so a lot of testing and a lot of work and a lot of worry and to make that happen. And then the surface mission, a year and a quarter on Mars, collecting up the samples with all of our amazing instruments. I think I covered most of this already. We need to be able to drive much further distances than Curiosity was able to, and so we've engineered in a lot of things about that, which I'll explain in a second. And let's see what's next. Okay, so these are the instruments on the Mars 2020 rover. I'll start with the mast. The mast, I'm not sure if you guys can see my arrow here, but this is the remote sensing mast, and it has stereo cameras that we use for engineering, for figuring out driving and picking samples and getting range to the ground. And then we have 2 instruments, a very capable pair of zoom cameras, zoom stereo cameras in different spectra. And then I'll just call this a laser zapper. It's called the SuperChem instrument. It has a laser that's strong enough to vaporize rock or material on the ground, and then a spectrometer that looks at the spectra of the vapor. And so you can see what things are made of out to about 12 meters away from the rover without having to drive over there, unstow the arm, get a sample, put the sample inside the rover. So it's kind of like a remote sniffer, sniff areas on the ground all around the rover. At the end of the robotic arm are these 2 spectrometers that I mentioned, and we could place the arm, and then overnight they can go to work in doing a little grid pattern to analyze the very, very up close, high proximity to the surface. One of my favorite instruments is RIMFAX, which is a ground penetrating radar. So with that, we'll be able to look underneath the surface at solid layers, and somewhere between 5 feet and 100 feet, depending on the terrain that we're driving over, we'll be able to see solid objects and things underneath. And that's a team in Norway that's doing that with glaciers already. And then META is an incredible weather station for wind and humidity and pressure and dust in the air. And then MOXIE is the oxygen generation experiment, creating oxygen from carbon dioxide. And I'm sure some of you have noticed this little helicopter flying up here. That is not green lit for this mission yet, but we're still working on it, and it's looking promising that we will that little helicopter will catch right to Mars on the rover, stowed underneath the rover's belly, and then it's going to be a technology demonstration for flying a vehicle on Mars for the first time, first of all, which, if you think about it, is pretty extraordinary. And then we'll also be able to get pictures from it from altitude and look at those. But really, it's a technology demo, so it is not a for sure thing that it's going to Mars yet, but it's still in the mix. And I think I already mentioned that we're going to be drilling samples and caching them in these little tubes. So this is all the hardware associated with that, the arm out the front, the drill bit, a bunch of different drill bits, and a drill bit holding station, and then a whole system for managing the tubes, the caches, because we have to make sure that they're contained well and that the rover has a place to store them until we're able to eject them so that they can be gathered later. So this is a picture of our sample caching tube and an example of a sample. These are a few slides talking about how far we want to be able to go to explore 2 giant regions of interest and little sub-explorations. And so I'm the deputy surface lead, and so we've spent a lot of time engineering how to drive faster and farther and do everything more efficiently so we can get to the scientific areas that are very interesting and get amazing samples as opposed to spending all our time in one small, non-interesting area of Mars. So compared to MSL, which is Curiosity, we need to, in the same time, 1.25, 1.25 Martian years, we need to cover at least 50% more distance and get 20 drilled samples instead of 6 drilled samples. So we need to up our game on efficiency. And so our rover basically has a coprocessor that can do all the vision processing, the stereo processing that I showed you earlier by kind of like a graphics gaming card that goes along with the computer. And so we'll be able to drive about 80 or 100 meters per hour instead of 12 meters per hour. What you're seeing here is the final 3 landing sites where we will be landing. This started many more, and then there was a big landing site workshop that anybody and everybody can attend, and they do, and pitch their view on why a certain landing site should be the place where we go. And then at the end of the landing site workshop, they narrowed it down. They narrowed it down to 8, and then 6 months ago, somewhere about that, they narrowed the 8 down to 3, and then later this fall we're going to pick the landing site, which actually will be a big help for the engineering team because they won't have to be engineering for all these differences in temperature and lighting, different things that are a big difference from these different sites. Just checking time here. So I think you saw some of this in the animation, but everything that JPL is designing, building, testing, and will be running is here on this slide. There's the cruise stage, which gets us to Mars, the back shell and the parachute, which is used during entry, descent, and landing, the descent stage, which is the rockets and the propulsion to slow us down, and the sky crane, and then the heat shield at the bottom, which comes off, and then the rover itself. And then we run the rover for at least 1.25 Mars years. Some of this hardware is being assembled right now. We're just over 2 years out from launch, and so that's the descent stage on the left that you see there, and the cruise stage on the right. You see guys in bunny suits working on those. They have to be clean and make sure we're not sending a bunch of human hair and hand oil to Mars, so that when we discover things on Mars, it's not our contaminated stuff that we send from Earth. And here's more pictures of those items. This is a test, a driving test. Call it an engineering model. It's a copy of the vehicle that has the right weight as if we were on Mars. So it weighs less on Earth because Earth's gravity is greater, and so we drive in different terrain and different slopes and over different things and avoid obstacles using this to see how Mars 2020 is going to do on Mars. So this is a slope with a kind of a tough sandy terrain. All right, and then we've already covered that. So I will show you one more video here and then kick it open to Q&A. And Alex can remind me how we're going to do that. All right, so I described to you that we need to be able to drive much further, much faster on each Martian day. And so this is a prototype of our autonomous obstacle detection and avoidance software running on that coprocessor with an FPGA. For those of you who know what that is, it's dedicated hardware for running those vision algorithms. And what you're going to see is in this test, they tell the vehicle to drive across the yard to the right side of the screen, and it can't get there because there's all these obstacles in the way, and so it needs to plan paths to get around all the obstacles. So this is sped up. But watching this video is a big win for me because instead of taking 8 hours to get across the yard, it was done in more like 1 hour, an order of magnitude faster than what we're able to do with Curiosity. And what you see on the bottom left is a prototype graphical representation one of the guys here is working on that shows the results of the path planning algorithm, and it's the obstacle map that you get from the range maps from the cameras and the arc that it's picking on each round of execution. And so the rover is only stopping to adjust its wheels on the curve that's going to be driving on. It's other than that, it's just processing fast enough to be able to continuously drive through this terrain. It's also looking for what we call negative obstacles, which is like a cliff or a big hole, so that it doesn't accidentally drive off a cliff or into a big hole that's a problem. So it'll avoid those as well, and you can see those in red there. And then as it gets more information on the left, as it turns, it sees an area that will work, and then it drives down the hill after making a few decisions. So just to be clear, there is nobody driving this rover. It did all of this work, computation, calculation, and navigation by itself over about a 35, 40-minute period. And so if all goes well, this is exactly what will be happening on Mars in about 2.5 years. All right, so that is everything that I wanted to show you all in a big blast of information. I hope you got something out of that. So I'll open up to a Q&A here, and I guess I'll click on the panel. So I don't know if we're going to do this with audio or with typing, Alex. But
it's going to be, the first part is that there were some people that voted, submitted questions online to start with. And so I'm going to, and then some other people voted them up. So I'm going to go ask you the questions that people asked online first. And then some of the participants have already put their hand up, and if we get to those questions, they'll be typing their questions in. I'll allow them to type them, and I'll read them to you.
Great, thank you.
Yeah. So anyway, so the first question really has to do with your background. You talked a lot about it already, but some of the other questions that they had for you is if somebody is wanting to study robotics now, what advice would you give to them?
I would say, and I'm glad that was asked because I wanted to say something about this earlier. There is nothing stopping you from studying robotics and working on robots right now, today, period. And you'll notice that I didn't say right now, at your college, or before you get to college, or when you get to college. You can there's a program called First Robotics, which high school students work on, and you can go and be a mentor for them and work on robots with them. There's kits online. If nothing else, you can buy a Lego robotics kit, which are actually amazing these days. They have pneumatics, air pressure, and motors, and you can program them, and pretty much every aspect of robotics are captured in the Lego robotics kit. So that's the big overall punchline. I think there's some sub-questions there on colleges and what to do at colleges and where to go and where to look. So obviously, look for anything that's happening at your community college, ranging from clubs to a professor who might have, some side projects for you to work on with them. There are community colleges that have that. And then, of course, do your research and scope out undergrad degrees at four-year schools and graduate degrees, master's degrees, and find the schools that have good robotics programs with lots of people attending. And you don't need to focus on the professors that are the best, that have the most papers. For example, in California, there's two schools called Cal Poly San Luis Obispo and Cal Poly Pomona. And Cal Poly San Luis Obispo, their whole thing is about hands-on learning. And so they have a bunch of professors there that all they do is teach undergrads hands-on stuff, lots of mechatronics and robotics. So find the undergrad schools that interest you, and the robotics degrees that they have. Check out the labs that they have there, because when you're there getting your degree, you can also go get a part-time job working in a robotics lab for a professor on his research. Or one of the things that I did at UCLA that I forgot to mention, I got credit for a class in my senior year by, I don't know what to call it, I forgot what it was called, but basically I worked up my own project with a professor. This is as an undergrad, before I even had a degree, and we worked out what I was going to do for a semester, and I got full engineering credit for that. And what I ended up doing was taking these old robots from iRobot, getting them working again, and documenting that. And then I got them following a wall with a very simple IR sensor. So I think those are some ideas for you, and hopefully that answers that question.
Awesome. Thank you so much. The next question I have is more about the rover, the way it travels on Mars. And you answered some of it earlier about as far as that, but beyond, because you showed the video about it being autonomous versus pre-programmed, but what type of navigation instructions do you give it? And then as far as weather, is it able to go all the time during weather, or do you pause it because of the terrain changing so much during a windstorm or any other type of weather that may be out there?
Again, glad that question came up, because I meant to say something about this earlier in my blast of information here. There's a fundamental thing about exploring the solar system and the rest of the universe that a lot of people aren't aware of, and that is how far away planetary bodies are from each other. So it takes light, at the speed of light, somewhere between 4 and 18 minutes to get to Mars one way. And that's important because that's how fast our radio signals get to our spacecraft and our rovers. So if you went to Toys R Us before it closed down here and bought a remote controlled car, launched it to Mars, and it somehow survived the landing, and you had a very powerful radio on it, so you could remote control your remote control car, and you had a little camera so you could see what it was doing, you'd hit the joystick and go forward, and it would take almost 20 minutes at different times based on the orbits, 20 minutes before the car started driving, and then it would take another 20 minutes for the images to update that are coming back to you. And that's just Mars. Pluto is over 5 hours one way. And then I just saw a news article about a star that we've just looked at with the Hubble telescope that I think it was 9 billion light years. So,
yep.
So when we're trying to control these things that we send out to explore, there's a very basic thing, which is they must be able to do things by themselves because it takes so long for our instructions to get to them. So back to Mars for a second. Well, actually, let me just say this. So the spacecraft that went by Pluto and did a flyby, I think, last year, spent 9 years getting out to Pluto, and then the flyby happened in like a few days, and so everything needed to be pre-programmed and pre-timed. So back to Mars, the cadence, the routine that we actually command our rovers with is we send one set of instructions in the morning when it wakes up through a very low bandwidth connection, and so it gets its instructions for the day, and then it warms up its motors, turns everything on, and then goes to carry out its instructions. And then halfway through the day, an orbiter goes by, and we download a lot of information through the orbiter because we can get much more data via the orbiter rather than directly from the rover, because it takes more power to send the data directly to Earth. And then at the end of the day, the end of the Martian day, another orbiter goes by. Kind of. It varies based on the orbiter patterns, but we get about 2 passes a day from the orbiter and get all the imagery and the results of the driving and the results of the sampling with the spectrometer and everything we're trying to do. We get that information down, analyze it all, figure out the plan for the next day, and then send them the next plan. So to answer your questions about driving, we tell it to do. Sometimes we're doing a day where we're not driving at all. We're just doing remote samples of the environment with the laser zapper, or I should call it the SuperCam instrument, not the laser zapper, or the Mastcam camera, or with the arm. But some days we're just driving. So I'll talk about a day where we're just driving as far as we can to get to that next region of interest. The rover planners, the rover drivers, look at the stereo camera imagery, and they can get good range data out to about 50 meters. So about 150 feet. And so they can plan a drive just automatically driving 150 feet, although it's using the camera to figure out how much it's slipping because the wheels slip, in particular if we're on a slope or something. And then at the end of the 150 feet, that's as far as we can tell it to go with the information we have on Earth at that point. So then we tell it to continue driving with autonomous navigation, avoiding obstacles, and if it gets too tilted, then stop and return, phone home for help. And if a motor jams, then stop, and 50 other things that we're watching autonomously that it's keeping an eye on. Voltage is getting too high, current going too high, current voltage going too low, temperatures going too high, a motor getting too hot, lots and lots of things. If anything like that goes wrong, it stops, reports the error back to us. But if all goes well, it continues driving autonomously, avoiding obstacles, and finding the best path that it can to a target that we gave it, just a 3D target in space, and until it runs out of battery voltage and we have to recharge for the next day of driving, or we don't have enough light to continue driving. So that was a very long answer, but I think I answered most of it. Oh, there was something about weather. Most of the time, we don't have to worry about big changes in weather causing us problems because the atmosphere, the pressure over there is very light compared to Earth. It's less than 100th of the pressure. So if you fanned your face on Mars, you would feel about 1/100th of what you're feeling on Earth. So we can just drive through wind going by, and sometimes we'll see a big dust storm, and we'll adjust, point our cameras down or something so we don't get too much dust on things. But most of the time, we can just do whatever we want and ignore the weather. Just measure the weather and report it. All right, I think I covered that question.
All right. No, so Ed, I turned the chat on real fast. Unfortunately, I think we're just going to be able to get to one other question. So I was wondering, Robert, if it's going to be okay that if the students submit the questions to me, if I'm able to get them to you, would you be able to answer them, and then I could post those answers to them?
Yes, I will. I will do my best. I'm about to go on vacation in 24 hours, so
Okay.
might be
Awesome.
a little delay on the answers coming back, but I will.
That is
I
fine.
answer at least the first answer for every question that you send me, Alex.
I appreciate that. Thank you so much. So, Eduardo, you can go ahead and ask your question real fast, and we will get to that one. So, Eduardo goes, I understand that autonomous behavior is important to the rover. And I just lost my, there we go. The rover, so, yeah, so how often, do humans take over control of the rover? Is the rover supposed to never require human piloting for either navigation or experiments? Are there any ideas to development to boost the signal in time and reduce the signal lag that you mentioned from the Earth to Mars? So I think you answered most of those, except for maybe about the, are there any ideas in development to boost the signal time? Or is there a way to...
So we're always working on making things happen autonomously and safely because of this but inherent difficulty with the physics of communicating with Mars. Sometimes we'll plan a weekend drive where the operators tell it drive for 3 days autonomously. So that's no human piloting for 3 days. And then to boost the signal time and reduce the signal lag that you mentioned from Earth to Mars. So that's a tough one on the lag and the time because we are literally communicating with our rovers and our spacecraft at the speed of light, maybe slightly less as the radio wave travels through atmosphere on the way out and the way in. But basically, our commands, our signals are getting there at the speed of light. And as you all know, as a society and as a race, we have not cracked sending things anywhere in any way faster than the speed of light. But I will say, in regards to the small amount of data that we're having to deal with, we only get like 500, between 500 and 1,000 megabits per day. Don't hold me to that, but if I took a few pictures, a bunch of pictures with my phone at the highest resolution, that's all that we can send back in one day. So I will say this, that hopefully we'll come up with something like a laser communication system. There's a lot of difficulties there in working it out, but with a laser light system sending communication with ones and zeros by turning the laser on and off very fast, we'll be able to increase the amount of data that we get back and hopefully can send by orders of magnitude. It's like the difference between your DSL modem and like the optical, forgot the name of it, the optical communications over the internet. So
Awesome.
if we can crack that, then yeah, fiber optic. If we can crack that, then we can at least get 100 times, 500 times more data down and pictures and information every day from Mars.
Well, thank you so much, Robert, as far as taking the time out of your day to sit down here and talk with us. A lot of people are already saying thank you and how wonderful it was. For those of you that had questions, I'm sorry that we didn't get a chance to get to them, but I am going to go ahead and there's the email again. Please, please, please go ahead and email those questions. We'll try and get them composed as quickly as possible and send them off to Robert. And Robert, please don't worry about getting them done before vacation. If you happen to get some done beforehand, great, send them my way. And then if you happen to have time when you get back, that would be great. They're here with us for another 3 weeks. So unless you're
Great.
going for 3 weeks.
No, unfortunately not. I see all the thank you scrolling by. Thank you guys for listening and for your questions. And just decide what you want to make or build, or the end effect of your your work every day in the future, and then just keep at it until you get there, and you will be happy, and life will be good. Or at least you'll have great challenges to work on that are tough. All right.
All right.
Thank you all, and I'll talk to you some other time.
I appreciate it, Robert. You take care. All right. That was cool.